So hello everyone, my name is Paulina, and today I will present a paper that actually I created together with Professor Christoph Lampert from Institute of Science and Technology, Austria. And the title is quite long, but I'll decipher it during this 15-minute talk, so don't worry. And the title is Lightweight Conditional Model Extrapolation for Streaming Data Under Class Prior Shift, and in short, LIMES. Some of you may know the explainability tool which is called LIME, but it's something different. This LIMES and this S at the very end is actually significant. So who I am? I'm a PhD student at Warsaw University of Technology, and I'm mostly working on deep learning, but in context of knowledge transfer, which is a broader term than just transfer learning. And I'm a member of MI2 Data Lab at the university, but I also have some international experience because I was doing some research internships in different places. Okay, so let me begin with a short question to you. We'll see whether it will work. So the question is, have you ever struggled to build a model when data set was highly imbalanced? You can raise your hand if that was the case. Cool, wow, it works. Thank you so much. You know, I was worried that just one person will raise the hand and yeah, it will be a problem then. Okay, great. So now a follow-up thing. So now you can imagine that the problem can get even more difficult if this class imbalance will change over time. And this is the problem that we decided to address in our study. Okay, so going back to the title. Now let's focus on the second part of it, so on streaming data under class prior shift. So what does it mean? Okay, so I guess most of you can imagine what streaming data is. This is a data that we generate all the time, and that is processed in real time. But what's the problem with such data? First of all, there's a lot of such data. And if we want to process it in real time, we have to be quick. But also, this data is mostly non-stationary. It means that some different changes are happening in this data. So what can happen? There are different drifts, but in my speech, I will focus on the last one. Yeah, on the last one. Here, oops, okay. So which is called class prior shift. And what does it mean? It means that the distribution of the classes is changing over time. So here you have the illustration. At the beginning, this ratio was 7:8, but now after the change is half-half. Okay, so how can we actually tackle such a problem? So we can think about this in different ways. Of course, we can build one model. And what will happen then? In most cases, due to the optimization scheme that we use, the model will learn to be good on average. So first it will learn how to solve one task, I mean one class distribution, then the model will experience another class distribution, and so on and so on. But in the end, it will just be okay-ish all the time, which is not what we want. And okay, I hope everything's correct. So this is not what we want. So the other approach is to actually decide a priori how many different scenarios, so different class distributions we will have, and just train different models, so have a pool of the models, and then just choose the model that we want, that we need at a particular time. But what's the problem with this approach? So if we have a scenario when this class distribution will change very often, then we'll need to have a lot of different models. So once again, it's not optimal. So what can we do? We can have one model, but the model that can be easily adjusted to different scenarios. So this is the scenario we have here. And this is the motivation behind the LIMES method. Okay, so now let's decipher the first part of the title. So lightweight conditional model extrapolation. Okay, so we already know that we want to have one model that we can adjust to different scenarios. And maybe some of you already have heard about something similar, which is called mammal network. In that case, we have one model, we train the weights, and we want these weights to be easily transferable, adjustable for different scenarios. And this moment of adaptation is happening during few gradient updates, most of the time just one. And what's the difference between the LIMES method? So it's kind of similar. We also want to have a general weights, but this adaptation step is done using analytical formula. So no additional gradient updates are needed. Okay, and now let's go into the math. I promise this is the only slide with math. Okay, so what we have here. First of all, we have the output of the basic classifier. So this is just a shorter version of softmax output. Okay, so now how we can actually go from the classifier that is trained for this class distribution to a classifier that will be suitable for another class distribution. So how to go from P to Q. Okay, we have a classifier that is ready to be used for the class distribution P. So what to do next? So we should do some assumptions that are reflecting the class prior shift setting. So what does it mean? In our case, it means, of course, that the distribution of the classes at the time that we have probability Q is different than probability P. So this is class prior shift. And also another fact is that the boundaries within our classifier are the same. It means that the probability Q of x given y is the same as probability P of x given y. Okay, and this is all of the assumptions that we have. So what we can do next? Next, we can apply a Bayesian rule. So we want to move from this distribution to this distribution. And I will not go into the details, but when we apply 2 times, actually, a Bayesian rule, we will see that we can calculate this new classifier based on the previous one by just multiplicating by something like this. Okay, but we know that this second term, this here, it does not depend on y, so we can just omit it for now. So we just stick with this part like the previous classifier times this part here. So later on, we can go back and decipher that this P of y given x is something like here. And when we do it, we can finally see that we can have a classifier, this new classifier, that is pretty much the same as the original one, but there's an additional term. This term C is actually just a subtraction of these 2 logarithms. So you can see that we can move easily from the P to Q distribution. Okay, and when we have this formula for the C, and C we call the bias correction term, we have 2 different distributions, and in our research, we claim that it can be done easily because, okay, this Q is a distribution at a particular time. This is a distribution that is changing over time, and this P distribution is a reference class distribution. This is this distribution that will always go from to different other distributions. So in our case, always, this P distribution is a uniform distribution over all classes. Okay, so this is all about the theory. Now let's move to the experimental setup, and maybe the results, I hope, will be actually convincing. Okay, so what was the setup? So we decided to analyze data that is experiencing quite a lot of changes over time, which is the data from Twitter. So we have data. We know what posts are issued. We know some metadata of the post, text of the tweet, and what we can predict. So we say to predict the country where the tweet was sent. And it seems like quite easy setup, but we also put some constraint on it. So we wanted to train a model in a continuous manner. So we didn't want to store any samples in the memory for a longer time. We just use it and just forget about this in this sense. And we wanted the system to be lightweight. So it comes with like not using big networks, but also with not storing the data set. Okay, and about the data set. So first of all, we collected data using a free Twitter streaming API. And the data was from April to July 2020. And as I said, we wanted to solve the classification problem. And in our case, there were 250 classes. And some of you may ask, okay, but depending on some rankings or say some lists, there may be fewer countries. Actually, we decided to follow this one regulation. And according to it, such territories that feel independent, but maybe they are not now, they're also treated as a separate entity. And when it comes to the training data, we decided to do it in a most fair and, let's say, responsible way as we could. So we decided to create in total 60 different realizations. But what does it mean? So first of all, we divided the data into 2 splits. So this time, we treated as one part the data from the 1st to the 5th day of each month. This kind of split was called early. And the other from the 11th to 15th day was called lately. Also, there were 10 realizations. It means that we just randomly divided, after having this early and lately split, we divided into 10 different realizations each. First of all, there was a lot of data, so we didn't need to have everything for the classifier to be trained. And also we wanted to later assess what is the uncertainty and the error of the model. And moreover, we evaluated 3 different data sources. So as an input, we used just the text of the tweet. So that was one scenario. In another one, something that is called location. This is metadata that we have from the Twitter. But this is not something that can be easily like mapped to the countries. And also concatenation of the both. Okay, so what does it mean that there was class prior shift in the data? It means that if we have a look at the class distribution of the labels in time, so here we have the data from one day, and we can see this fluctuation. So let's say US, this is the blue line, so there's like a big minimum here. It means that at the beginning, people from US were tweeting, but then they went to sleep, so they were not tweeting. Then they woke up and were once again tweeting. So the goal was that we wanted to do the prediction on data from our T after having experienced previous data, so the data from time 0 to T-1. And of course, because of these variations, so different class distribution over time, also the difficulty of the task varied. So here, there were like a lot of different countries that were tweeting at the same time, and these probabilities were pretty much similar, so the task was difficult. Okay, and the last important step in the algorithm. So we already know that there was one component, which is called bias correction term, and we know how to calculate it, but we don't know, actually, how to get this Q distribution, because the data at the hour T is going to come to us, but as the hour is beginning, we don't know what's going to happen. So what we do, we do the extrapolation. So the only thing that we store, we don't store the data itself, but we store just the historical class distributions in a table. And then when we have experienced the data from time T-1, we search in a table for the class distribution that was the most similar to the class distribution from the time T-1. We find this, and then we take the next class distribution, assuming that this is the most similar case that will happen just in a moment. So this is our approximation, and this is what we use in this formula. And the pipeline, so, okay, we had the text of the tweet, we used the pre-trained transformer to do the embedding, and then there was a classifier with the ability to move to different scenarios. And the setup was very much similar to linear probing. Okay, and the most important part, so the results, whether it actually works or it's for nothing. So, trust me, it works, and here you can see. So here I present on the upper chart the results from the day March 1st to 5th. So the first 120 hours. And you can see here the accuracy. And here are the hours. And you can, okay, so there are different like benchmarking, some baselines. And the blue lines are the LIMES. Maybe you don't see it because it's always the best, but and also this incremental method is sometimes similar when it comes to performance, but in these valleys here, you can see that in the valleys, LIMES is always better than the incremental method. And these valleys are the moments where the task is the most difficult. And to make it maybe easier to analyze, we decided to do some kind of aggregation. So on this chart, we calculate the average performance over the day, so over the 24 hours. And here you can see that LIMES is very similar to incremental method. Incremental method is like the method that have just one model without any any bias correction term and extrapolation, therefore. And here we have minimum across a day. So these are the moments where we can see these valleys. And we see that when it comes to the minimum performance over a day, LIMES is much better than incremental. And why we actually care about this minimum accuracy? So here a very short anecdote. So when some people have to fill up the form assessing quality of some course, let's say, so what happens? In most cases, people that are the least satisfied with the course, they fill out the form. So actually, if we are a company, we should care mostly about these most difficult moments. This is why LIMES should be a good choice for a model. Okay, a very short sum up. So LIMES is lightweight. LIMES has two different mechanisms, bias correction term and extrapolation. And LIMES outperforms other baseline models, especially when it comes to this minimum performance over a day. And here's the implementation and the paper. If you're interested, please check it out. Yeah, thank you for your attention.